studying molecular structure, and investigating different type of reaction mechanisms, etc. So now let us start discussion discussing about from unit 1. So we will start from unit 1. So the unit 1 is electromagnetic radiation. So the first one is so we should know that what is electromagnetic radiation. So first we should know that what is that one, and electromagnetic radiation may be defined as the radiant energy which is transmitted through space at different velocities. It exists in various forms like visible light, radiant heat being easily recognized from which experience in our day-to-day life. The electromagnetic radiation, unlike sound, do not require any medium for transmission or propagation. So it can, without any medium, the electromagnetic radiation can propagate. And the velocity of the, so if that will propagate through vacuum, the velocity of the electromagnetic radiation is considered to be 3 into 10 to the power 8 meter per second. That is the velocity of light. The study of different ways in which the electromagnetic radiation can interact with matter is of great importance in chemistry and also for this paper. In order to understand the interaction, it is therefore necessary to have knowledge the properties of the electromagnetic radiation. So first we should know that what are the different properties of electromagnetic radiation. Before that, we should know that the wave mechanical model of the electromagnetic radiation. The electromagnetic radiation is considered to be sinusoidal nature. So this curve, so this is the graph of a sinusoidal curve. That is, it will vary like a sine function. According to the Maxwell theory, the electromagnetic wave can be divided into two different parts, that is electric field vector and magnetic field vector. Both the vectors are perpendicular to one another and also they will perpendicular to the direction of propagation. So now coming to the different characteristics parameter of the electromagnetic radiation, you can see that, so this is the origin, that means the starting point of the electromagnetic radiation, and this is the direction of propagation. And you can see the electromagnetic radiation contains two different field vectors, that is first one is electrical field vector and the next one is magnetic field vector. Both the electric and magnetic field vector are perpendicular to one another and also they are perpendicular to the direction of propagation. So first we will discuss about the characteristics parameters for electromagnetic radiation. So in order to discuss the characteristics parameters, or in order to quantify the different electromagnetic radiation, we should know the different point. So the first one is, and first of all, it is wave-like nature. So as the nature of the electromagnetic radiation is wave-like, and it is also called as electromagnetic wave. So in order to quantify the electromagnetic wave, the different parameters are there. The first one is amplitude. So what do you mean by amplitude? It is the maximum height to which the wave oscillates and equals to the height of the crest and or depth of the trough. So suppose consider any wave. Suppose this is the wave, any type of wave, and this one is the direction of propagation. We know that the waves contains conjugative crest and trough. Suppose this is the direction of propagation. This is the origin and this is the direction of propagation of the wave. So the wave contains So the maxima of the wave is known as crest, and the minima is trough. So if we'll take a if we'll consider the middle axis, suppose this one, if we'll consider the middle axis, the height of the crest is known as amplitude, and also the depth of the trough, that is also known as amplitude. Both are same. Now coming to amplitude, it is the maximum height to which the wave oscillates, and also equals to the height of the crest or depth of the trough. It is measured. It is a measure of the radiant power of the radiation. The radiant power means the energy of the radiation striking at a given area per unit time. It is denoted as P and related to square of its amplitude. So radiant power is known as P, and it is proportional to square of its amplitude. It is important to remember that the radiant power is not related to wavelength. It is related to energy of the wave. A closely related term is intensity of the radiation, which is denoted as I and define the radiant power per unit solid angle. Now coming to the next factor is wavelength. The next characteristics factor, that is known as wavelength. So it is the linear distance between two consecutive crests or two consecutive trough. Now suppose this is the direction of propagation, and let this is the wave. There will be, and the two maxima points. So the distance between two consecutive crests, the distance between two consecutive crests or the distance between two consecutive trough is known as wavelength, and it is also the distance of a complete wave. Complete wave means that will contain one complete crest and one trough. So the length of a complete wave is known as wavelength. You can also tell that the distance between two consecutive waves, the distance between two consecutive crests, or the distance between two consecutive trough, that is also known as wavelength, and it is denoted as the Greek letter lambda, and the unit of the wavelength is so as it is the distance between two consecutive crests or between two consecutive trough or the distance of a complete wave. So the unit of the wavelength is meter, centimeter, micrometer, nanometer, degree angstrom, and so on. And here there is the conversion between the different unit meter. 1 nanometer equals to 10 to the power minus 9 meter. Now coming to the next one is frequency. Frequency is denoted as nu, and it is defined as the number of crests or troughs that pass through a given point per second. Suppose this is the starting of the wave. Suppose this is the starting point of the wave, and let the wave is passing through x-axis like this. So this is the direction of propagation of the wave. Now suppose we will put a marker on the path. Any marker, we will put a marker. So the frequency is defined as the number of crests or the number of troughs. That means the number of complete waves passing through a given point. And as wavelength is known as length of a complete wave, and frequency is number of complete waves passing through a particular point per second. So frequency is inversely proportional to wavelength. That means if wavelength will be less, in 1 second, more number of waves or more number of complete waves will be passing through that point. So that's why wavelength is inversely proportional to its unit is per second, that is second inverse, and exactly, that is called as hertz. As wavelength is inversely proportional to frequency, or frequency is inversely proportional to wavelength, so frequency nu equals to some constant divided by wavelength, so that constant is the velocity of light, that is called c. So nu equals to c by lambda, where c is a constant, that is called velocity of light, and its value is 3 into 10 to the power 8 meter per second. Now coming to the next one is to quantify any wave, that is called wave number. It is equals to the number of waves present per centimeter distance or per unit distance. Now suppose this is the starting point. Suppose we will take a particular unit distance. Within that distance, the number of complete wave present is known as wave number. That means if the wavelength is less within that particular length of distance, more number of waves will be present, and hence it is the reciprocal of wavelength, and it is denoted as nu bar. So by the so relationship between nu bar and lambda is nu bar equals to 1 by lambda. Now coming to the next factor, that is called velocity. It is defined as the linear distance traveled by the wave in 1 second. Just like the definition of velocity, distance traveled by the wave per second. So the velocity in meters per second can be obtained by multiplying the frequency, because we know that the frequency is the number of complete waves passing through a particular point in 1 second, and again wavelength is the length of a complete wave. So that means if n number of waves will be passed through that particular point in 1 second, then its velocity will be the number of waves is frequency, then its velocity c equals to nu into lambda. So c equals to nu into lambda. So this is the relationship between, and from this relationship we can also find out lambda equals to c by nu, or nu equals to c by lambda. Now coming to energy. The energy of the electromagnetic radiation depends upon the wavelength and also depends upon the frequency, because wavelength is inversely proportional to frequency. According to Planck's theory, we know that E equals to h nu, and again we can put the value of nu, that is c by lambda, and hence E equals to hc by lambda. Here h is the Planck's constant and having value 6.626 into 10 to the power minus 37 joule second. And nu is the frequency, c is the velocity of light, lambda is the wavelength. So now in this table it is given the complete characteristics of a particular electromagnetic radiation. So the first one is wavelength, the relationship with wavelength, that is lambda. The unit of the wavelength is meter, micrometer, nanometer, angstrom, etc. Now coming to wave number, that is nu bar equals to 1 by lambda. So that's why the unit of the nu bar is meter inverse, centimeter inverse, nanometer inverse, etc. Now coming to frequency, frequency nu equals to c by lambda, and its unit is hertz or cycles per second or second inverse. Now coming to velocity, we know that velocity c equals to nu into lambda, and if the electromagnetic radiation will travel uh, in a vacuum, then the velocity of the electromagnetic radiation will be considered to be velocity of light, that is 3 into 10 to the power 8 meter per second. And after that, energy E equals to h nu, or that is equals to hc by lambda. The unit is joule. Now coming to electromagnetic spectrum. Here we have already discussed that the wavelength of a particular wave is inversely proportional to its frequency. So now coming to electromagnetic spectrum. Electromagnetic spectrum means arrangement of different electromagnetic radiations according to increasing order or decreasing order of wavelength or frequency. That means here you can arrange the different electromagnetic radiation according to increasing order of frequency, according to decreasing order of frequency, according to increasing order of wavelength, or according to decreasing order of wavelength. So that is called as electromagnetic spectrum. Here in the figure it is given the electromagnetic spectrum, and here you can see that the different wavelengths are arranged according to increasing order of wavelength. That means from shorter wavelength to longer wavelength. And the first one will come gamma rays. So it is having shorter wavelength. The next one is X-ray. After that, ultraviolet. Then visible light are colored. That's why the range of visible light is 400 nanometer to 700 nanometer of wavelength. And after that, infrared, then microwave, then the radio waves. And again, the radio waves are divided into two types, FM and AM. And after that, long radio waves. So here you can observe that the different electromagnetic radiations are arranged according to increasing order of their wavelength. So that's why if you consider according to frequency, it is according to decreasing order of frequency. That means from right to left, it is increasing order of frequency. That means X-ray having shorter wavelength or shortest wavelength and having highest frequency. And again we know that E equals to hc by lambda. H is a constant, c is the velocity of light, that is also constant, divided by lambda. So that means between the different electromagnetic radiations mentioned in this electromagnetic spectrum, the gamma ray is most powerful. That means most energetic. The most energetic is gamma ray. After that, X-ray, then ultraviolet, then visible, then infrared, then microwave, then radio waves. Now coming to polychromatic and monochromatic radiation. Polychromatic radiation means if the electromagnetic radiation spread over a range. In other words, if the electromagnetic radiation emitted by a source contains a number of radiations or different radiations with a different wavelength, then that is called as polychromatic radiation. And the monochromatic radiation, that we can generate or separate out radiation of a single wavelength. The electromagnetic radiations with a single wavelength, that is known as monochromatic radiation. Now coming to the quantum model of the electromagnetic radiation. The quantum model of the electromagnetic radiation can be explained by two different factors. The first one is blackbody radiation and the second one is photoelectric effect. So let us first discuss about blackbody radiation. So the blackbody radiation means, suppose we know that all the heated objects emit electromagnetic radiation, and the wavelength of this radiation depends upon the temperature of the object. For example, at a relatively low temperature, a metal rod emits IR radiation which cannot be seen, but we can feel the heat. As the temperature increased from suppose we will put a metal Fe rod in the furnace. As the temperature will increase up to 600 degrees Celsius, the color of the metal rod will become dull red color because it will emit more energetic electromagnetic radiation. That's why that is fall in the visible region. And when the temperature is still more, that is 2000 degrees Celsius, it will glow to white. White means it will contains the electromagnetic radiations with all wavelength. However, the energy radiated by a hot surface depends on its nature and surface area. Besides the temperature, apart from the temperature, another two factors are also there that depends upon the nature and surface area also. For a given area and temperature, a black surface radiates more energy per second than the polished surface. At a given temperature, the maximum radiation would be given out perfectly black surface, and the experiment observed data on the radiation intensity emitted at a different wavelength by a perfect black surface, that is called a black body, at a different temperature could not be explained by classical mechanics, that could be explained according to quantum mechanics. Now coming to the next effect is photoelectric effect. The photoelectric effect was observed by Hertz. He observed that when a light of a particular wavelength or light of appropriate wavelength falls on the clean surface of a metal plate in an evacuated vessel, a stream of electron is emitted. That means when a light of appropriate wavelength will fall on the clean metal surface in a evacuated vessel, then the light having sufficient energy to remove the surface electron from the metals, and hence the stream of electrons will be emitted. These electrons are called as photoelectrons, and the effect and the phenomenon emission of photoelectrons is known as photoelectric effect. Now coming to in quantum or particle model, the radiant energy is considered as stream of discrete particles or packets of or small packets of energy, that is called as quanta, whose energy, the radiation emitted by a substance are not in continuous manner that contains small packets of energy discontinuously. Suppose we will consider a particular packet of energy that is called a quanta, and the energy of a quanta is equal to E equals to h nu. And similarly, we know that E equals to hc by lambda, or alternatively, we can tell that E equals to hc nu bar. It is important to remember that the energy of the photon is not same as the radiant power. The radiant power includes the energy of the photon as well as the number of photons emitted. That is known as radiant power. And here you can see there is a question. A microwave radiation has a frequency of 12 gigahertz. What will be the energy of the photon considering this radiation? So just we know that E equals to h nu. Here the value of h, that is Planck's constant, we know, and here it is given, the frequency is already given, that is 12 gigahertz, means uh, uh, 12 into 10 to the power 12 second inverse. So that's why we can find out the energy accordingly. And then second, calculate the wavelength of the radiation. So the frequency is given, means the wavelength lambda equals to, or here we have calculated the energy. We know that E equals to hc by lambda, or lambda equals to E by hc. Energy we have calculated. We'll put the value of Planck's constant, then the value of c, that is the velocity of light, and we can find out the wavelength of the radiant energy is 400 nanometer. Now coming to the consequences of wave nature of the electromagnetic radiation. So here we have discussed the wave nature of the electromagnetic radiation, and both the classical model and electromagnetic and quantum model of the electromagnetic radiation. And after that we will discuss the consequences, that means the result of electromagnetic radiation. The first one is interference. So it is a very interesting phenomena observed by Thomas Young. He reported that the result of his famous double slit experiment on light, he observed that when a monochromatic light was made to pass through a closely spaced narrow slit and it fall on a distance screen of a series of dark and light bands will be observed. So now this is the screen, and here you can observe, and here a monochromatic light allowed to pass through the slit of the screen. So there will be two slit will be there. So if the monochromatic light will pass through the double slits or the two slits, we can observe both constructive and destructive interference. So what do we mean by constructive interference? You can see, you can understand both. So the figure describes the schematic representation of interference of different waves. Suppose these are the two waves passing through the slit, and if the two and if the two waves will be merged such that the amplitude of the resultant wave equals to summation of the amplitude of the two waves, then this type of interference is called as constructive interference. You can see, so this one is the first wave, the red one is the first wave, and the second red is the second wave. And when the two waves will in phase, then the resultant wave having amplitude, there will be double of the amplitude of the wave, and this type of interference is called constructive interference. But when the two waves in out of phase, in the second figure you can observe when the two waves are out of, so that means in particular this, if you consider a particular wave front, suppose this one is a particular wave front, at this position we see that the crest of the first wave fall and the trough of the second wave fall at that particular wave front, and hence there will be destructive interference and the amplitude of the resultant wave will be zero. So this type of interference is called a destructive interference, and the first one is called constructive interference. That means if the amplitude of the resultant wave will be doubled, then that is called constructive interference, and if the amplitude of the resultant wave will be zero, then that is called destructive interference. And apart from that, any other type of interference are partially constructive and partially destructive. Now coming to the next phenomenon is diffraction. You might have experienced the formation of waves in the pond. Suppose we will take one example: formation of waves in a pond of still water when disturbed by throwing a stone. That means we will throw a stone to a pond and the still water, there will be formation of wave in the still water. Have you ever seen the changes in such a wave when it encounter a small barrier or a narrow opening? If you have observed, you will recall that these waves bend or change their direction of propagation when some barrier will be there or when some obstacle will be there. So the phenomenon of change of direction or the phenomenon of bending of waves, the phenomenon of bendings of wave around the corners of a sharp barrier through the narrow opening, that is called a diffraction. Electromagnetic radiation show this type of phenomenon. The consequence of diffraction can be observed by placing a photographic plate on the path diffracted in the path of a diffracted radiation. The occurrence of the pattern of alternative bright and a dark band is characteristics of the diffraction. Suppose this is the monochromatic radiation passing through a particular direction. Now if we put a photographic plate in some position, we will get bright band, and in some other position we will get dark band. So this is due to bending of the electromagnetic radiation when that will strike at a different obstacle. Now coming to the next one, that is called a transmission. When the radiation passes through a transparent medium, its velocity is found to be reduced as compared to that of vacuum, because we have already discussed that if the electromagnetic radiation will passing through a complete vacuum, then the velocity of the electromagnetic radiation will be equal to velocity of light, that is equal to 3 into 10 to the power 8 meter per second. But when the radiation passes through a transparent medium, then the velocity is found to be reduced as compared to than that of vacuum. So this is due to, because if vacuum will be there, there will be no other species or gaseous atoms or gaseous molecules or gaseous ions present on the path of the electromagnetic radiation. But if there will be no vacuum, due to the presence of different gases, gas molecules, atoms, etc., the electromagnetic radiation will interact with this type of gaseous particle, and hence there is a reduction of velocity depends upon the nature and concentration of the gases, ions or molecules present in the medium. When the radiation interact with atoms or molecule present in the medium, it result periodic polarization, that means deformation of their electron cloud. So in the absence of any absorption, the energy required for polarization is retained only momentarily, that is 10 to the power minus 14 to 10 to the power minus 15 s. And it is re-emitted without any alternation and the substance returned to its original state. Since the re-emission of the radiation is delayed due to sometimes, then the radiation takes a little longer or to travel through a distance, and hence its velocity will be decreased. So the extent of interaction of electromagnetic radiation with matter can be expressed in terms of a term that is called refractive index. So the refractive index, that is eta I, can be defined as C equals to nu I, where eta I is the refractive index of the radiation of a given frequency I, given frequency nu I, and C where nu I, c and nu I are the velocity, c and nu I are the velocity of the electromagnetic radiation in vacuum and in the medium respectively. So the radiation of the so the variation of the refractive index. So refractive index equals to velocity of the electromagnetic radiation in vacuum, that is c, divided by velocity of the electromagnetic radiation in that particular gaseous medium, that is Vi. So refractive index equals to c by Vi. So this variation of the refractive index of a substance with wavelength and the radiation, that is called as the dispersion. If the refractive index increases gradually with increasing frequency, it is called as the normal dispersion. And if there is a sharp change in the refractive index, then that is called as anomalous dispersion. Then coming to refraction. When a beam of light traveling through air falls on a glass at an angle, it abruptly changes its direction, or simply what, it will bend. A similar effect is observed when a light emerges back into an air after passing through the glass. In general, when the radiation falls on the interface of the two transparent media, then the difference. So that means there will be two transparent media will be there, and the density of the two transparent media will be different. And if light will be passing through it, then it will be abruptly change its direction, and this phenomenon is called as diffraction. For example, this phenomenon is called as refraction. For example, suppose here this is medium 1 and this is medium 2. Both the mediums are transparent, but the density of the two mediums are different. So in the medium 1, suppose the incident ray will be like this, and when that will pass through the medium 2, so that will bend. So this is called a refracted ray. And suppose this is a normal to both the mediums, and here you can see, according to you can see from the figure, according to Snell's law, sin theta 1 by sin theta 2 equals to eta 2 by eta 1, which is equals to nu 1 by nu 2, where v1 by v2, where theta 1 theta 2 are the angle of incident between the incident ray and the angle of refraction between the refracted ray. So, and eta 1 and eta 2 are the refractive indices of the medium 1 and 2. Now coming to the next phenomenon of consequences of electromagnetic radiation, that is called a reflection. When a radiation traveling in a medium traveling in a medium is incident on a medium of different refractive index, a fraction of the radiation bounce back to an angle equals to angle of incident of the radiation, that is called as reflection. Suppose one electromagnetic radiation will be travel in a particular medium, and if the radiation will be allowed to travel in another medium, then when that will enter into another medium, all the electromagnetic radiation will not pass through it. Some of the electromagnetic radiation will be a fraction of the radiation bounce back at an angle equals to the incident. Suppose this is the boundary between the, so this is medium 1 and this is medium 2, and here this is the angle of incident from of one electromagnetic radiation from medium 1 to medium 2, and all the electromagnetic radiation passing through medium 1 will not pass through medium 2. A fraction of the electromagnetic radiation, suppose this one is theta, will rebound back with same angle of incident. This will be theta. This phenomenon is called a reflection. So this one is so this is the incident ray and this is the reflected ray. So according to the equation given for the reflected light, PR by P naught equals to eta 2 minus eta 1 square divided by eta 2 plus eta 1 whole square, where P naught and PR are the radiant power of the incident and reflected beams. P naught not stand for incident and R for reflected. N1 and N2 are the are the refractive indices of the two mediums. So this is medium 1 and this is medium 2. So this is the diagrammatical representation of the reflection and refraction. So here this one is reflection and refraction. Sorry. This one is refraction and another phenomena that is called a reflection. This one is reflection. Now coming to scattering. The interaction of electromagnetic radiation with matter causes retention of the radiant energy by the atoms, ions or molecules due to their polarization. If the polarized particles are small, then destructive interference of the re-emitted radiation eliminate and re-emitted radiation in all the direction other than the original path of the light. Then we observe the radiation transmitted in all altered direction, and this experimental observation however revealed that a minute fraction of the radiation is transmitted in all directions. This phenomenon is called as scattering, and the radiation is called as scattered radiation. Now coming to polarization. So when ordinary radiation created by vibration of electric charges, ordinary electromagnetic radiation means that will vibrate in all possible planes, in all directions. That means the electromagnetic radiation will oscillate in all possible directions. Thus, a radiation consists of a bundle of electromagnetic waves in which the vibration or vibration means oscillation are equally distributed among infinite series of planes perpendicular to the direction of propagation. That means, the electromagnetic, if we consider any ordinary electromagnetic radiation that contains a bundle of electromagnetic waves that will oscillate in all possible directions, and there will be infinite number of planes. So radiation which is vibrating more than one plane is called a unpolarized radiation. So from the figure you can see that this is the direction of propagation of a unpolarized light. So here you can observe that, so the unpolarized light, so that will oscillate in all possible planes. In that can oscillate in this plane, that can oscillate in this plane, that can oscillate in infinite number of planes in the direction of propagation. But when that will pass through a polarizer, you will observe that the electromagnetic radiation will propagate or will oscillate in only one plane. That is called a plane polarized light. So this one is called plane polarized light, and before passing through the polarizer, the light is called unpolarized light. So this phenomenon is called as polarization. Now coming to interaction of the electromagnetic radiation with matter. So we have already discussed the quantum mechanical description of the electromagnetical electronic structure of atom and molecule consisting of matter in the lower classes, and these have unique set of quantized energy levels available for them. These are arised from the motion of electron around the nucleus or the electrons in an atom and molecules present in the allowed or permissibly energy states. That means, so if you will consider a single atom, the different electrons are present in different energy levels, and if you will consider a molecule, the different electrons will also present in different energy levels, but the energy levels of a molecule will be quite complex as that of the energy level of isolated atom. However, in case of molecule, the rotation and vibration motions are also there. They are also quantized. So if we consider isolated gaseous atom, the different electrons are present in discrete energy levels and they are quantized. And similarly, in case of molecule, so in case of atom, there will be no rotational energy, no vibrational energy. Only electronic energy levels are there, and in case of isolated gaseous atom, the different electronic energy levels are quantized. But if you consider molecule, in addition to electronic energy level, the molecule can also undergo rotation and vibration. That means rotational and vibrational motions are also there, and these motions are also quantized in addition to this electronic energy level. So the allowed energy level, which is the least energy, is termed as ground state, while the rest of the energy levels are called as excited state. So here you can show, this is the schematic diagram showing the energy level of a molecule. So if we consider the energy level of atom, only discrete energy levels are there, different energy levels are there like this. Discrete energy levels are there like this. But if we consider the energy levels of a molecule, so these are electronic energy, only electronic energy levels will be present for isolated gaseous atom. But in case of molecules, in addition to this electronic energy level, some other energy levels are there. So these are called as rotational energy level. You can see these are rotational energy level, these are vibrational energy level. So that means for ground state, there will be rotational vibrational energy level. For fast excited state, there will be also rotational vibrational energy level. Similarly, for next second excited state, there will be rotational vibrational energy level. And hence, the schematic diagram showing the different energy levels of a molecule is quite complicated as that of the different energy level for isolated gaseous atom. For isolated gaseous atom, you can observe single discrete energy levels of atoms, and the transition of this energy state may be brought about the absorption of photon or suitable energy. That means if the molecule or if the matter will absorb electromagnetic radiation of a particular energy or suitable energy, so these molecules will undergo transition from ground state to excited state. So the energy difference between the two states can be calculated as del E equals to E2 minus E1, where E1 is the ground state energy level and E2 is the excited state energy level. So del E equals to E2 minus E1, that is equals to h nu, where h is the Planck's constant having the value 6.626 into 10 to the power minus 34 joule second, and nu is the frequency of the electromagnetic radiation that causes this type of transition, or that means the frequency of the electromagnetic radiation absorbed by the matter, and hence that will undergo transition from ground to excited state. So here that is the diagram showing the energy change during transition between the energy levels. So these transition energy levels may be vibrational transition, may be rotational transition, may be electronic transition, depending upon the nature of the electromagnetic radiation absorbed by the sample. Now coming to the next one is absorption. At a given temperature, different species, that may be atoms or molecules, are distributed among the allowed energy levels in accordance with Boltzmann distribution. So that means the suppose we will consider a particular sample. The particular sample contains large number of atoms or molecules. That means if we will consider 2 gram of hydrogen molecule, that means that will there will be Avogadro's number of hydrogen molecule. That means 6.622 into 10 to the power 23 hydrogen molecules. So at a particular temperature, different large number of species will be there, and the large number of species all are not present in the ground state. Some are different species or different particles are distributed among the different allowed energy levels of that sample, and in according to Boltzmann distribution law. So according to Boltzmann distribution, so that is a statistical distribution. According to statistical Boltzmann distribution, Ni divided by N naught equals to e to the power minus del E by kt, where Ni and N naught represent the population of the ith level and the ground state. N naught equals to population of the ground state, and Ni is the population of the ith excited state. Population means the number of particles present. So that is population means that so related to number of particles present. So that means N naught equals to number of particles present at ground state, and Ni is the number of particles present at ith excited state. Now according to the Boltzmann distribution formula, Ni by N naught equals to e to the power minus del E by kt, where del E is the difference of energy of the ground state and excited state, and K is called Boltzmann constant, and T is the absolute temperature. Now let us calculate the population of an energy level having energy 2 kilojoule per mole relative to energy. So here a particular example is given. So Delhi equals to EF by EI, EF minus EI. So that is equals to 2 point. So it is given 2 kilojoule per mole. That means 2 into 10 to the power 3 joule per mole divided by that is Planck's constant divided by Avogadro's number. So that will give rise the energy of a particular species. And here if we put this value, we can find out 0.4484. That means this implies that for every 10,000 species at ground state, there are 4,000 for every 10,000 species present at ground state, there are 4,484 species at the level having energy 2 kilojoule per mole relative to it. So now coming to the different type of spectrum, absorption and emission spectrum. Here we will discuss the different types of the two types of spectrum, that is called absorption and emission spectrum. Let us see what happens when a polychromatic radiation is made to impinge upon a sample containing atoms or molecules. So that means you will consider a particular sample and polychromatic radiation will be allowed to fall on that sample. One simply possibility that it will get transmitted unaffected through the sample. There may be, so there will be different possibilities. The first possibility is that the electromagnetic radiation will be transmitted unaffected through the sample, and the other possibility is that the radiation coming out from the sample is devoid the certain frequencies. That means in the latter case, the missing frequencies are said to be up. Suppose one electromagnetic radiation will be passed through a sample that contains large number of atoms or molecules. By nature, there will be two chances. If the electromagnetic radiation will transmitted unaffected through the sample, and the other possibility is that if according to its characteristics, if the sample will absorb electromagnetic radiation of a particular wavelength, when the electromagnetic radiation will coming out from that sample, a particular wavelength will be, so radiation of a particular wavelength or a particular frequency will be missing from their spectrum. Only those photons are absorbed whose energy matches with the difference of energy of the two energy states of the sample provided by transition among these levels. So according to this figure, you can see, so this one, suppose this is the source of electromagnetic radiation and that will allow to pass through the sample. So let the sample contain some different atoms or molecule and having the characteristics of absorbing electromagnetic radiation of different particular wavelength. So after passing through the sample, it will allow to fall on photographic plate. Otherwise, if will observe the electromagnetic radiation through prism, you can see that there will be certain black lines will be there. Black lines means the according to the characteristics of this sample observe the frequency of this particular position. That's why you will observe black line. And here you can see this is the source of electromagnetic radiation. No sample will be there. Only the electromagnetic radiation will be allowed to pass through a prism to observe a spectrum. So in this spectrum, you can find there will be no missing frequency of light will be there. So this type of spectrum is called as continuous spectrum. There will be no missing of frequency. But in the second figure, due to presence of observing species on the path of the electromagnetic radiation, you can see particular black lines are there. That means the electromagnetic radiation of that particular frequency is missing from the spectrum. This is called as absorption spectrum. And the absorption spectrum again can be divided into two types, that is called atomic absorption and molecular absorption. So if you observe atomic absorption, a line spectra will be there according to that figure. So let us consider the simple case of absorption of electromagnetic radiation by gaseous sodium atom. So if the electromagnetic radiation will be allowed to pass gaseous sodium atom, according to its characteristics, the sodium atom will absorb two radiations at 1 at 5 589 nanometer and other one at 589.6 nanometer. That means these two electromagnetic so these two electromagnetic radiations having frequency 589 nanometer and 589.6 nanometer will be missing after passing through the sodium gaseous sample. And similarly, the next one is molecular absorption. So the molecular absorption again, because we know that for molecule the different energy levels are composed, but for atoms the energy levels are only electronic energy level. For isolated gaseous atom, the different energy levels are only electronic energy level, but for molecules the energy level composed of electronic, vibrational, and rotational energy level. So according to the principle, all the three types of energy levels are quantized and occur on the excitation with radiation in the UV visible, IR, and microwave. So the electronic energy deals with UV visible spectra, the vibrational energy deals with IR spectra, and the rotational energy deals with microwave spectra. So this is the simplified energy level diagram showing the regions of observing band spectrum in the molecule. That's why for molecule, for isolated gaseous atom, you will find line spectra, but in case of molecules, you will observe band spectra due to presence of different types of energy levels. So here this is the sample of IR spectrum. So IR spectrum details we will discuss in unit 3 or 4 in the next class. So from the IR spectrum we can see that, so this is the wavelength of different electromagnetic waves passing through the sample, and at that position that there will be observance of the electromagnetic wave and the corresponding transmittance will be there. So that means at the position where the molecule will not observe the electromagnetic radiation, there will be transmitted around 90% or 100%. Theoretically that will be 100%, but practically here it is showing 90%. But the wavelength which is observed by the sample according to its characteristics, its transmittance will be sudden decreased to around 10 or 5 or 2%. So when the electromagnetic radiation will allowed to pass through the sample due to absorption of particular wavelength, there will be peak position, and if will in the other sense if will tell there will be decrease in transmittance, and that will give rise to different peaks. So that is the origin of IR spectra. Now coming to the other type of interaction, that is magnetic field induced absorption. We know that every particle such as electrons or nucleons are there, electrons or protons are there. They are also just like electrons are circulating around the nucleus, and also it is circulating around its own axis, that is called spin of electron, and similarly there will be spin of proton. When subjected to external strong magnetic field, the interaction between the internal and external magnetic field gives rise to additional quantized energy level. Apart from these three different quantized energy level, there will be additional quantized energy level due to spin of electron and proton. The difference in energy of these levels is very small, and the transitions are brought about by absorption of the radiation of longer wavelength, and the transition among the energy levels generated due to interaction of nuclear magnetic moment with the applied magnetic field are assigned as nuclear magnetic resonance. And similarly for electron spin, so this is for nuclear spin, that is called nuclear magnetic resonance NMR, and for electron spin, that is called ESR, that we will discuss in details later. So now coming to emission spectra. So here we have discussed the different types of absorption spectra. So the emission spectra is very simple. Suppose a particular sample is excited due to observance of due to suppose a particular sample is excited by electric energy, or by heat, and or by thermal energy. So then the particles present in the sample will move into excited state, and the lifetime of the particles in the excited state is very short, and they will again come back to the ground state by emitting electromagnetic radiation. That means the sample will absorb either heat energy or electric energy, and will go to excited state, and after that if that will come back to the ground state by emitting electromagnetic radiation, And if the electromagnetic radiation will allowed to fall on a photographic plate or will allowed to pass through a prism to observe the spectra, you can see that complete uh, black background is there, and within the background some bright lines are there. That means according to the characteristics of the sample, that will emit electromagnetic radiation of these particular wavelength, not in continuous spectra. So that will emit electromagnetic radiation of some of these particular wavelength, so that you will observe in the photographic plate. So when there will be no emission, the photographic plate will be completely black, and due to emission of particular wavelength, so there will be bright line on the black background. So this type of spectra is called as emission spectra. And similarly for atom, you will find line spectra. Line spectra means for if you observe the emission spectra of isolated gaseous atom, if you observe the emission spectra of isolated gaseous atom, only line spectra will be there just like this. That means discrete lines of particular wavelength you can observe on black background. But for molecules, there will be band spectra. Band spectra means there will be a combination of electronic, vibrational, and rotational energy levels. That's why for molecule we will observe band spectra. Now coming to continuous spectra, the continuous spectra are caused by solid substances. So when solid substances are heated, it is the characteristics of the temperature of the emitting surface rather than the bulk of the material. These type of spectra are produced by condensed solid substance give rise to atomic or molecular oscillation. So heated solids are used in the radiation source in the analytical instrument involving IR, visible, and UV radiation. And another two type of spectra are there, that is called fluorescence and phosphorescence spectra. So the emission spectra of atom and molecule discussed above in the energy of the emitted region is same as you the excited. So that means the energy of the emitted is also same as the energy of the excited. But in some atomic and molecular system, due to their characteristics, the emitted radiation is a different frequency than that of the excitation radiation. So these are either due to fluorescence or due to phosphorescence. Then coming to the Raman spectra. So the Raman spectra, when the radiation interact with a matter at a part of it gets scattered. So if a monochromatic radiation is used, then the scattered radiation of the same frequency as the incident radiation. If wavelength or frequency of the scattered radiation is similar to the wavelength or frequency of the incident radiation, these type of lines are called, so relay lines are relay scattering. However, it is observed that in case of radiation, some type of in some type of scattering, the frequency of the incident radiation is different than from the frequency of the scattered radiation. That means the frequency of the scattered radiation is different from that of the frequency of the incident radiation. So this type, that means the frequency of the scattered radiation may be increased, or the frequency of the scattered radiation may be decreased than that of the frequency of the incident radiation. So this type of interaction is called as Raman scattering, and the details of the Raman scattering will discuss in the corresponding unit. So coming to the overall spectroscopic methods based on the wavelength range and typical quantum transition involved. So here you can see Mossbar spectra. Mossbar spectra having so if the sample will observe electromagnetic radiation in the gamma ray, so that is also called as gamma ray spectroscopy. That means it's very energetic radiation. If the sample will undergo interaction with gamma ray, that means very energetic radiation, you can observe Mossbar spectra. And hence there will be nuclear transition, that means change of the nuclear configuration will be there. And similarly, if the sample under investigation will interact with electromagnetic radiation in the range of 0.1 to 100 angstrom, that is in the range of X-ray range, so then diffraction, absorption, emission, or fluorescence spectra will be observed. And similarly, if the sample undergo investigation interact with electromagnetic radiation in the range 10 to 180 nanometer, then UV absorption spectra will be there. and if the sample will interact with EM with 180 to 780 nanometer, then UV and visible absorption, emission or fluorescence will be there. And if the sample will undergo interaction with electromagnetic radiation of wavelength range 0.78 to 300 nanometer, and scattering will be there. If scattering will be there, that is called Raman scattering, and if absorption will be there, that is called IR spectra. And if the sample undergo investigation will interact with electromagnetic radiation of wavelength 0.75 to 3.75 nanometer, then the molecule will undergo, if the sample will be gaseous sample, that will undergo rotation, then we will observe microwave absorption spectra. And for NMR, the wavelength range is 0.6 to 10 to the power 0.6 to 10 meter, and we will observe NMR spectra. And similarly for ESR, the wavelength is around 3 centimeter. So this is about the introduction part, and after the introduction part, we will move to the details discussion of various type of spectroscopy. So the first chapter after the introduction, the first chapter is UV visible spectra or UV visible spectrometry. So now we'll discuss the UV visible spectrometry. So the unit 2 is UV visible spectrometry. So now coming to because we have already discussed in the introduction part. So first we'll discuss the origin of UV visible spectrum. We know that the absorption of radiation in the UV visible region of the spectrum is dependent on the electronic structure of the observing species, like that may be atom, that may be molecule, ions, or complex. So in the unit 1, we have already discussed that if the sample will contain isolated gaseous atoms, then the absorption and emission spectra will be quite simpler, and you will only observe line spectra. But in case of molecules, ions, and complexes, we can observe band spectra. So the absorption spectrum of atomic species consists of a number of narrow lines that arises as a consequence of transition among the different energy levels, atomic energy levels. But in case of molecule, the electronic, because in case of isolated gaseous atom, that means in case of atom only electronic energy levels are there, but in case of molecules, so the electronic, vibrational as well as rotational energy levels are there, and all are quantized. So a given electronic energy level has a number of vibrational energy level, and similarly a given vibrational energy level has a number of rotational energy levels. So in case of isolated gaseous atom, we can observe line spectra, while in case of molecules, due to the presence of electronic, vibrational, and rotational energy levels, we can observe band spectra. When a photon, when a photon of a given wavelength interact with the molecule, it may cause a transition among the electronic energy levels if its energy matches with the different of these energy levels. So due to this due to such type of transition, the sample in the gaseous and vapor phase, the spectrum contains number of closely spaced lines consisting of consisting what is called a band spectrum. So in case of molecules or complexes, we can observe closely spaced lines. So that's why that is called a band spectrum. We can see, these are very closely spaced lines are there between the electronic energy levels of the atom. We can find out the vibrational energy levels, and within vibrational energy level we can find out rotational energy levels. So very closely spaced lines are there. So in case of molecules and complexes, we will observe band spectra, that is called band spectrum. Now coming to the characteristics of suppose you can see, so here in this figure, that is the representation of UV spectrum in vapor phase. So here the UV spectrum of a particular sample in vapor phase. So in the vapor phase, you can observe that the sample will observe wavelength of a particular wavelength. So that's why different sharp peaks are there. When same sample will be present in the solution, that means in the solution phase, we can observe a broad peaks are there. Now coming to the characteristics of UV visible spectrum. In order to obtain the UV visible spectrum, the sample So here we will take just 2-3 minutes of a gap. After that, again we will continue. So just stay on here. So we will take just 2-3 minutes of gap. After that, we will continue. Okay, so now I will so resume the discussion. So here the discussion is characteristics of UV visible spectrum. In order to UV visible spectrum of a sample, the sample in order to obtain the UV visible spectrum, the sample is ideally so radiated with the electromagnetic radiation varied with a range of wavelength. So in order to get the UV visible spectrum of a particular sample, the sample, because we know that we don't know the characteristics of the sample, so the sample will be allowed to irradiated with a electromagnetic radiation of a varied range of wavelength. A monochromatic radiation, that is a radiation of single wavelength, is employed at a time. This process is called as scanning. So the amount of the radiation absorbed at each wavelength is measured and plotted against the wavelength to obtain the spectrum. Thus, a typical UV visible spectrum of a plot or wavelength or frequency versus intensity of absorption will be there. That means during scanning, the unknown sample is allowed to interact with different electromagnetic radiation of a range of wavelength. So, according to the characteristics of the sample, if the sample will absorb, so that means the sample will allow to interact with the a different range of single wavelength electromagnetic radiations. Now, if the sample will according to its characteristics, if that will absorb electromagnetic radiation of particular one, two, or three different wavelength, then observance will be there. So then, but according to the characteristics, that will not absorb electromagnetic radiation of all wavelength. That will absorb electromagnetic radiation of particular different wavelength. So here, according to the figure 2.1b, you can see this is 2.1b. Yes. So when electromagnetic radiation is allowed to pass through the sample, you can see that the sample will absorb wavelength of suppose this is 242 nanometer, and after that that will again absorb 248 nanometer. After that that will again allowed to absorb 252 nanometer, then 258 nanometer, like this. That means the sample will not absorb frequencies or wavelength of all radiation, that will according to its characteristics that will absorb frequency or wavelength of particular radiation, and hence there will be peak. So figure 2b, the axis of x-axis indicate the wavelength of the observed, therefore that is marked in the wavelength through sometimes and in the graph we can plot in the x-axis either wavelength or frequency. Generally it is taken as wavelength. The y-axis, in the other hand, represent the intensity of observation and generally represented the terms of observance. That means the UV spectra, the UV spectra of the substance are characterized by two major parameters. That is the position of the absorption band or the position of the peak, and second one that is called a lambda max, the position of the absorption maxima, the position of the maximum of absorption band, that is called lambda max. That means here in this spectra, so the corresponding wavelength position, this one is called a lambda max, this is called lambda max. So that is the position of the maximum of the absorption band, that is called a lambda max, and the intensity of the band. So these two factors are used to characterize the sample through UV visible spectra. The lambda max refers to the wavelength of the most observed intensity of the band. The lambda max refers to the wavelength of the most observed radiation and is measured in the difference in the energy levels involving in the transition. The intensity, of the other hand, indicates the probability of the transition. That is, whether the transition is allowed or not. It is also measured in the concentration of the observing species. Now coming to the observing species, the characteristics of the UV visible spectrum depends upon the structure and concentration of the observing species in the solution. That means the samples present in the solution. So then we will discuss the different types of observing species are there, because the sample undergo investigation that may contain organic molecules, that may contains inorganic molecules, that may contains polymers, that may contains um, um, any type of other substances may be there. So accordingly, uh, there different observing species are there. So first we'll discuss if the observing species will be organic molecules. That means the sample under investigation. If the sample under investigation will be organic molecules, then molecular absorption in the UV visible radiation depends upon the electronic structure of the molecule. The wavelength of the radiation absorbed by the organic molecule is determined by the difference in energy between the ground state and various state excited electronic state of the molecules. Now bonding in the organic molecules. For this knowledge of bonding in the organic molecules, that the constituent atoms are bonded whether through pi or sigma bond. In addition to that, some other type of non-bonding electrons are also there, that is called lone pair of electrons. If the organic molecule, if nitrogen, oxygen, sulfur, halogen, some heteroatoms will be there in the organic molecules apart from carbon and hydrogen. So if only carbon and hydrogen will be there, that means the atoms are bonded through sigma or pi bond. And if nitrogen, oxygen, sulfur or halogen, some different heteroatoms will be there, then non-bonding electrons are also present, or lone pair of electrons are also present. These non-bonding electrons are denoted as N. And for sigma bonding electrons, they are denoted as sigma. For pi bonding electrons, they are denoted as pi. So the generalized molecular orbital energy level diagram and possible transition of the different organic compounds is given here. So We know that the pi bonded electrons are energetically very less, so that in the, so they will present in the lowest energy level. Sorry, the sigma bonded electrons are energetically very less, so they will present. So they are stable, so they will present at the lowest energy level. And the next higher energy level is pi bonding pi bonded electrons, and the next energy levels are non-bonding electrons, and the next one is anti-bonding, that is pi star anti-bonding, and the next one is sigma star anti-bonding. So as a rule, the transition occur from the highest occupied molecular orbital HOMO, that is called HOMO, to the lowest unoccupied. So the electronic transition will take place from the highest occupied molecular orbitals to lowest unoccupied molecular orbital. You can observe that the electrons may present in sigma bonding molecular orbital, may present in pi bonding molecular orbital, may present in non-bonding molecular orbital. So that means the transition of electron will take place from HOMO, that is from sigma, from pi to n, to non-bonding, that is to pi star or sigma star. So if the transition will take place from sigma to sigma star, so this is the most energetic electronic transition, and the next will be when the transition will take place from sigma to pi star, and the next one will be when the transition will take place from pi to sigma star, then n to sigma star, then pi to pi star, and the lowest energy will be consumed when the transition will take place from n to pi star. So the six possible transitions are there. So we will discuss one by one. So let us discuss the first one, that is pi to pi transition. So these transitions are observed in the molecule containing pi electrons are occurred at a wavelength approaching near UV region. The hydrocarbon containing double bond, triple bonds are typical example. For example, ethylene observes at 170 nanometer, and the conjugation unsaturated. So if in the organic molecule conjugation will be there, conjugation of uh, conjugated double bonds will be there, or conjugation of unsaturation will be there, then there will be further increasing lambda max. For example, for ethylene, it will absorb at 170 nanometer, but in case of buta-1,3-diene, that means there will be pi conjugation will be there, that will absorb at longer wavelength, that is 217 nanometer. The effect of conjugation is quite important in aromatic molecules. For example, if the single ring aromatic absorbs the vicinity of, so for a, if you consider a single aromatic isorin, that will absorb at still higher wavelength, that is 250 nanometer. And if you will consider naphthalene, that means two condensed aromatic benzene rings, two fused benzene rings, that will absorb at 300 nanometer. And in case of anthracene, that is three fused benzene rings, that will absorb at 360 nanometer. That means the if the conjugation, if pi conjugation will increase, the substance will absorb at longer wavelength. Now coming to the next transition is N to pi star transition. These transitions are observed in the molecules containing lone pair or non-bonding electrons. Uh, in such a transition, one of the non-bonding electron may be excited into an empty pi star orbital. The energy required for these transitions are lower than that of the pi to pi star transition, and results absorption in the ultraviolet and visible region. The presence of atoms or group containing n electrons can cause these type of changes in the spectrum. Thus, nitrogen, sulfur, halogen atoms present in the organic molecule tend to move absorption to higher wavelengths. The pi to pi star transitions are generally intense, while n to pi star transitions are weak, because the intensity of this type of transition depends upon the population of the excitation. For example, acetone exhibits a high intensity pi to pi star transition at 195 nanometer, and a low intense n to pi star transition at 274 nanometer. So due to presence of lone pair of electron or non-bonding electron over the oxygen atom, n to pi star transition will occur, but due to its low population, it will be low intense, and but the transition will occur at higher wavelength. You can see the spectra of ethylene like this. So the ethylene will show two different types of peaks. One, the first peak is due to presence of carbon oxygen pi bond. So there will be pi to pi star transition. So this is for acetone. So due to pi to pi star transition, the lambda max will be 195, and here the population will be very high, and here the lambda max will be around 195 nanometer. And similarly, another type of transition will be there due to presence of non-bonding electron over the oxygen atom, that will occur at lambda max 274 nanometer, but the intensity will be less. So here these are the absorption characteristics of the common chromophoric group. So here another type of factor is there, that is called as chromophore. The only molecule like to absorb light in the 200 to 800 nanometer region contains pi electrons and may also have atoms in the non-bonding electrons. So the number, if the number of if atoms with a non-bonding electron will be more, then the wavelength will be extended into longer wavelength. Then the wavelength of then the wavelength of absorption will be at longer wavelength. Such groups absorb light in the UV visible region referred to as chromophores. The chromophore means coloring. So as the wavelength will increase, or the as the molecule will absorb at longer wavelength, so it will coming from the ultraviolet to visible. So if the wavelength will increase and fall in the visible region, then the sample will look like color, and the spectra will look like color. So that's why that is called color bearing. Color bearing means chromophore. However, the term of chromophore now not limited to color, that is, but also general way the groups which are responsible for causing absorption of electromagnetic radiation between 175 to 800 nanometer, that is called as chromophore. So here some different chromophores are there in particular examples, due to which the lambda max, the position of the wavelength absorption will be increased. Now coming to inorganic species, a large number of inorganic salts containing atoms with electrons in the d orbitals, giving rise to weak absorption band in the visible range, and the ions and the complexes of the element of the first two transition series belonging to the group under color. So the color of this species is due to transition among the d orbital, the complex formation of these ions with solvent molecule or other ligands leaves the degeneracy of the 5d orbitals. So when the sample will undergo interaction with electromagnetic radiation, then due to presence of the ligands, the d orbital degeneracy is already removed, and that's why there will be transition of electron from the lower d to higher d. That means from T2g to EG, or from E to T. So these type of transitions are called as DD transition. Due to DD transition, some inorganic compounds contains transition metal atoms are colored in nature. And similarly, similar principle can be applied to the lanthanides and actinides, and these are also colored due to FF transition. The next one is charge transfer complex. Many times a given compound that is transparent in the UV region starts absorbing after interacting with another species. This happens if one of the species uh, of an electron donor group interact with species of an electron acceptor group. So when the two species bind to each other, then the resulting species is intensively colored. So this is due to formation of a complex between the two species. Such complex is called a charge transfer complex. That means the complex will contains two groups, and the one group is electron donor group, and another group is electron acceptor group, and the charge transfer spectra will be obtained. So if one of the species with an electron donor group, and that will interact with species, some other species having electron acceptor group. So this type of spectra is called charge transfer spectra. For example, the blood red color of the complex ion, that is thiocyanate iron. So this one is thiocyanate iron FeSCN 2 plus, is due to formation of charge transfer complex. So here the charge transfer will take place. So the radiation absorbed by this product or complex called the charge transfer of an electron of an orbital in the donor of an orbital of the acceptor. So this has been schematically shown in figure. So due to charge transfer spectra, the molecule thiocyanate iron, the species FeSCN2 plus will absorb at a wavelength of around 470 nanometer. And if a large number of chelating ligands are used in different types of organic compound, we know that chelating so ligands are there. So the intense color of such material chelates is often due to the charge transfer transition. That means there will be transition of electron from the HOMO to LUMO of the donor atom, similarly HOMO to LUMO of the acceptor atom, and hence if one species will contain say atom with electron donor and another species contains atom with electron acceptor, and if both the species will undergo formation of a complex inorganic complex, you can observe due to homo lumo combination, due to donor acceptor combination, the energy gap between the homo and lumo will be decreased, and hence that will fall in the longer wavelength, and hence that will looks like color. That is called charge transfer spectra. Now coming to the principle of UV visible spectrometry. So in the principle we will discuss how the spectra will be observed. In a typical observation, spectral measurement of monochromatic radiation is made to fall on the sample taken in suitable container. So in the UV visible measurement, the sample will be taken in a container that is called a cuvette. So in the cuvette, the UV visible electromagnetic radiation of UV visible range, that means from 200 to 800 nanometer, will be allowed to pass through the sample, and for every irradiation monochromatic light will be there. That means first 200 nanometer will pass through the sample, then 200.5, then 200.1, then first 200 nanometer, after that 200.5 nanometer, then 201 nanometer, then 201.5 nanometer, then 202 nanometer, then 202.5 nanometer. That means individually monochromatic lights will allow to pass through the sample which present in a suitable container, that is called cuvette. In such a situation, part of the radiation is reflected and a part will be absorbed and a part will be transmitted. So the intensity of the original radiation is P naught, and if the intensity of the reflected will be PR, and if the intensity of the absorbed radiation is PA and the intensity of the transmitted radiation is PT, then P naught equals to PR plus PA plus PT. The effect of the reflection can be compensated by passing equal intensity beam through the solution and through the solvent containing same or similar container, and comparing the transmitted radiation. We can now write the equation as that P naught equals to PA plus PT. So the intensity of the transmitted light is measured and found to depends upon the thickness of the observing medium of the concentration beside the intensity of the incident radiation. This dependence form the basis of the spectrometric determination, and that will be governed by Lambert's and Beer's law. So now we'll discuss the Lambert's law part one. So the law stated that studied the law studied the decrease in the intensity of the radiation when it passes through a substance, and made following observation will be there. The amount of monochromatic light absorbed by the sample is proportional to the intensity of the incident light. That means the ratios of the intensity of the ratio of the intensity of the transmitted and incident light is constant. Second one is the intensity of the transmitted light decreases exponentially when thickness of the substance through which the light is passed increases. So if thickness of the substance will increases, then the intensity of the transmitted light will decreases exponentially. So Let P naught represent the radiant power of the incident light. P represent the radiant power of the transmitted light after passing through the slab of thickness B. Consider a small a slab of thickness dx. So here this is the slab of thickness B through which the light will be passed, and P naught is the radiation. P naught is the intensity of the incident light, and P is the intensity of the light after transmitted through the sample of thickness B. And if we'll examine this observation through a very thin portion, that is the portion may be dx, right? Consider a small slab of thickness dx, then the change in power or within this small thickness range, the change in intensity or change in power will be dpx, that is proportional to the incident light px. So dpx is proportional to px px multiplied by change in thickness. So dpx is proportional to px into dx, or dpx equals to some constant minus k px dx. So why minus sign is there? Because as the thickness will increase, the intensity of the transmitted light will decrease. So that's why there is a negative sign is there, where k is the proportionally constant, and the negative sign indicates that the radiant power decreases or the intensity decreases. And from this equation we can write dpx by px equals to minus kdx. And if we take logarithm both side with limit from p naught to p, then the intensity from 0 to b, sorry, the intensity from p naught to p, and that means the intensity will be p naught when the thickness will be 0, and the intensity will be decreased to p when the thickness will be p. So we will take the limit from p naught to p, and in the right hand side the thickness 0 to b. And if we're taking integration of this equation, we can find out ln p by p naught equals to minus kb. So this equation 2.3, that is a mathematical expression of Lambert's law, or simply that is called as Lambert's law. So changing this equation to base 10, so if we change, so this is an equation of natural logarithm, and if we convert this equation to base 10, we can write log p naught by p equals to k by 2.303b. So here negative sign is removed, because in the left hand side it is there, that is ln p by p naught, but here it is so written ln p naught by p. So that's why the negative sign is removed. So log p naught by p equals to k by 2.303b, and here k is one constant and 2.303 is constant, so that will give rise to another constant k dash b. Note that the ratio p by p naught has been inverted to remove the negative sign in the Lambert's law. Now coming to Beer's law. So the Beer's law explain, it is found that the relationship between intensity and transmitted light and concentration was exactly same as found in the Lambert's law. So here, so in the Lambert's law, it is observed the relationship between the transmitted light and thickness of the medium. And here in the Beer's law, the transmitted light thickness as well as the concentration of the medium. Consider the monochromatic light of intensity px traversing any thickness of a solution of single absorbing substance of concentration C. If C changes by a small amount from dc to C plus dc, then the change in transmitting power dpx is proportional to incident intensity px and dc. We can write dpx equals to, dpx is directly proportional to px dc, or dpx equals to some constant minus k double dash px dc, where k double dash is proportional constant and negative sign indicate that the radiant power or the intensity decreases with absorption. So from this equation we can write dpx by px equals to minus k double dash dc, and similarly taking logarithm both sides we can find out the equation like this. So this is called Beer's law. Uh, 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 we can find the equation like this: log 10 p naught by p equals to k double dash by 2.303 c. And if we combine both Lambert's and Beer's law, we can write log p. So from Lambert's law, we can write log p naught by p equals to k dash b. From Beer's law, we can write log p naught by p equals to k double dash by 2.303 c. And if we combine both Beer's law and Lambert's law, we can write log p naught by p equals to abc, where a is constant, uh, that is taking combining two constant k dash, k double dash, and the numerical value 2.303, and that is called the absorptivity, or that is also called as extinction coefficient epsilon, whose value depends upon the unit of concentration used and the function of the wavelength of the monochromatic light used. So the concentration generally expressed in terms of gram per ml, or B in terms of centimeter. Therefore, it has a unit centimeter inverse, gram inverse, decimeter cube. However, the concentration is expressed as mole per decimeter cube, and B in terms of centimeter, that is called molar absorptivity. If molar term will be there, that is called molar absorptivity or molar extinction coefficient, and it is expressed as in case of molar sample, that is expressed as epsilon or molar extinction coefficient. Its unit are called centimeter inverse, mole inverse, decimeter cube. So the modified expression of the Lambert's-Beer's law can be written as log p naught by p equals to epsilon bc. So here the term log p naught by p is called absorbance, and that means absorbance a equals to log p naught by p. The expression of Lambert's-Beer's law then becomes log p naught by p equals to observance a equals to abc or epsilon bc. The observance way a is related to important term, that is also called as the transmittance, which is defined as the fraction of the incident light transmitted by observing medium. Mathematically, transmittance equals to T equals to P by P naught. It is generally expressed as a percentage of transmittance, and hence percentage of transmittance percentage T equals to P by P naught into 100. It is also related to observance A equals to minus log T. And here one question is there, so this is a direct question. You can find put the value in the Beer's law, so that can be solved according to Beer's law. And similarly, here another question is there that can be also solved by taking the percentage of transmittance from the above equations. Now coming to deviations from Beer's and Lambert's law. So there will be so if the sample will obey Beer's and Lambert's law, then there will be straight line. And in many cases, a plot of observance versus concentration is is expected to be a straight line passing through the origin. However, this is not always true. There are certain limitations. The law does not hold good for species under every conditions. Many times, instead of a straight line, a curvature of plot may be observed as shown in the figure. So if there will be upward curvature, that is called positive deviation. If there will be the curvature will be downward, then that is called negative deviation. So this type of deviation from the Lambert's-Beer's law will be there due to presence of electrolytes, due to presence of hydrogen ion concentration, and so and other causes are due to complexation or association or dissociation of sample. Suppose we will take calcium cobalt chloride, they will undergo association, so the cobalt chloride will be blue color, but in the solution they will undergo association to form a complex tetrachloro cobalt complex, so that will be blue in color. And similarly, non monochromatic nature of the radiation, if the radiation will be non monochromatic, then this type of deviation will be there. The deviation may be positive or may be negative. And another cause of deviation another cause of deviation is the concentration of the analyte. According to Lambert's-Beer's law, there will be no deviation if the observing substance will be in very less concentration. So a plot of observance versus concentration of the observing substance will be straight line when A, B are constant and the path length always held constant at some factors. That means when the for at higher concentration there will be chance of deviation. Now coming to another factor is temperature. The temperature is not considered as heat. important factor since ordinary all the measurement are made at a constant temperature, that means in a laboratory where the temperature will be constant. Now coming to the instrumentation for UV visible spectrometry, the five essential components of the UV visible instrument are that a suitable radiation source, a wavelength selector, sample holder, radiation detector, that is a transducer, that is one electronic apparatus, and signal processing or output device. So the first one is radiation source, then that will pass through a monochromator to obtain monochromatic radiation. Then the monochromatic radiation will pass through a sample cell containing the sample under investigation, and after that the sample will observe particular wavelength, but that will not absorb all the wavelength, and after that that will the observed wavelength will be detected through the transducer, and that will, and finally we will get signal for output. And here the different radiation sources are there. First we will discuss about the radiation source. For measurement of UV region, electric discharge source such as hydrogen or deuterium lamp are used. In these excitation, the gaseous molecule is brought about by passage of electron through the gas at low pressure. A hydrogen lamp is commonly used in the spectrophotometers and give line in the wavelength of range of 160 to 375 nanometer. And the radiant power of the hydrogen, the radiant power or the intensity of the hydrogen lamp is low, and these are nowadays these are replaced by deuterium lamp. So this is the source of UV. Now coming to the source of visible, the source, because for nowadays for source of UV deuterium lamp is used, and the wavelength range of the deuterium lamp is 160 to 375 nanometer. That means when the scanning will take place more than 375 nanometer, then the light source will be changed. That will get so the light will be coming from source of visible region. In the beginning of development of instrument of colorimetry work, sunlight was used as the source of visible region. But nowadays, the modern instrument use tungsten filament lamp as the radiation source. This consists a thin coiled tungsten wire and sealed at an evacuated glass tube. So this gives radiation in the range of 350 to 2200 nanometer. As the output depends upon the voltage, tungsten lamp is energized by 6 to 12 volt, uh, energized by a 6 to 12 volt storage battery or by output constant voltage transformer. Now coming to wavelength selector. So the wavelength selector, the spectroscopic measurement we need to a narrow band of wavelength of light. This enhances the selectivity or sensitivity of the instrument. Less expensive instrument use filter to isolate radiant energy and provide a broad band of wavelength. In many applications, we need to continuously vary the wavelength over different range. This can be achieved by monochromators. Most modern instruments use monochromators that employ a prism or diffraction grating as the dispersing medium. The selection and use of the filter and monochromator is described like this. So the first one is absorption filter, a low cost instrument in low cost instrument catering to measurement in the visible range. Colored gas filters are used as the cutoff of the undesirable wavelength. A typical, so that means in case of low cost instrument, color gas, color glass filters are used to stop the undesirable wavelength. But a typically a typical filter is a color piece of glass which absorbs light of certain wavelength and allow that of the other to pass through this. You know that white light is made up of seven different colors, that is called Vibgyor. So if we will take a light that contains more, of all wavelength, so that will become white, and that will contain seven basic colors, that is violet, indigo, blue, green, yellow, and orange range. So these 7 colors add to give white light back. When white light falls on an object, a part of it is absorbed and the rest is transmitted. These transmitted components add up to give the observed color of the object. So that means when the light will contains all the 7 basic colors, that will white. But if the light will pass, if the white light will pass through the sample, then according to the characteristics of the sample, if the sample will absorb a particular light from the source, that will looks like color. So the absorbed component and the observed color can be again add up to give white light. So these are therefore called a complementary to each other. An object of a particular color looks of the color. An object of a particular color looks of that color because this color is transmitted and its complementary color is observed. So you can see this is a color wheel. That means if white light will pass through the sample, if the sample will absorb red color from the white light, that will looks like green. It's complementary, opposite side. If the sample will absorb blue color, that will looks like orange. If the sample will absorb yellow color, that will looks like violet. So that means if the white light will pass through the sample, and according to characteristics of the sample, if the sample will absorb a particular color from the white light, it will looks like its complementary color. So that can be detected through color wheel. Then coming to the monochromators. So different monochromators are there. First one is prism monochromator. Initially prism monochromators were used, but nowadays grating monochromators are there. So the uh, function of the monochromators is that will allow to pass the light or the electromagnetic radiation at a particular wavelength through the sample, and we will see whether the electromagnetic radiation of a particular wavelength will be absorbed or transmitted. If that will transmitted, then the next wavelength electromagnetic radiation will allow to pass through the sample. If that will absorb or transmitted, gradually from a range of 200 nanometer to 2200 nanometer wavelength will pass through the sample and will observe the sample will observe which wavelength of light. And now coming to sample handling. So the UV visible absorption spectra are usually determined in vapor phase or in solution phase. So generally that is not observed in solid state. So that is observed in either vapor phase or solid phase. In order to take the UV spectrum of the analyte.
The call
Hello.
Hello.
Mr. Nirmal Kumar, please mute. Mr. Nirmal Kumar, please mute.
Hello.
அது மட்டும் வர மாட்டேங்குதா?
இல்ல மத்த யூடியூப் எல்லாம் சவுண்ட் வருது.
அப்படியே அது அது இப்படி அப்படி வருது. சவுண்ட்னா சவுண்ட் அவுட் பண்ண ரெண்டு ஸ்கிரீன் வரணும்ல.
நான் இது சவுண்ட் வருது. Hello dear Nirmal Kumar, please mute.
இந்த கால்ல இருக்கு இந்த இது வளைச்சிங்க.
Hello Nirmal Kumar, please switch off your phone.
நீ
Hello.
கால்ல இருக்கியா? இந்த இதுல வீட்ல.
Mute. Hello.
அது ஓபன் பண்ணு
Hello.
போயிட்டு ரெட் மீட் எடு. நான் இப்ப யூடியூப் வளைச்சிது. என்ன இருக்கு? கால் கால்
Okay, so now coming to the sample handling part, the UV visible absorption spectra are usually determined for vapor phase or in solution phase. In order to take the UV visible spectrum, in order to take the UV visible spectrum of the analyte, it is taken in a cell that is called as cuvette, that we have already discussed. That cuvette which is transparent to the wavelength of light passing through it. That means the one, so the opposite side of the cuvette will be transparent, so that, so this is one the figure of a cuvette, so that the light will passing through the transparent side. And these type of cuvettes are used for solution, and for gaseous sample these cuvettes are used. A variety of quartz cuvettes are available for spectral determination in the vapor phase. These are varying path lengths, are equipped with inlet and outlet. For measurement of solution in the visible region, the cuvettes are made on the glass and that can be used. But for UV and visible, the cuvettes are made up of quartz cuvettes. So nowadays, quartz cuvettes are used for measurement. Now coming to detector, so the UV visible spectrophotometer connected with the, so the detector may be photo tube, that may be PMT, that may be photomultiplier tube. So the detector is an electronic device that consists of photo emissive cathode and an anode in an evacuated tube with a quartz window as shown in the figure. So that is the evacuated tube, and so that will detect the observed so radiation. And the different types of detectors are photo tube or PMT, that is called photo multiplier tube, and diode array detectors are nowadays used. Now coming to the signal processing and output device, the electrical signal from the transducer is suitably amplified and processed before it is sent to the recorder to give an output. The subtraction of the solvent spectrum from that of the solution is done electronically. So the output plot between the wavelength and the intensity of the absorption is the resultant of the subtraction process and is characterized by the absorption of species. Now coming to type of UV visible spectrophotometer. So there are two different types of UV visible spectrophotometer, three different types of UV visible spectrophotometer is there. The first one is single beam spectrophotometer, and the second one is double beam spectrophotometer, and the third one is photodiode array spectrophotometer. Generally, the second and third type of spectrophotometers are used because in first type of spectrophotometer, the instrument contains a single beam of light. The same beam is used for reading the absorption of the sample as well as the reference. But in case of double beam spectrophotometer, two different beam of monochromatic light will pass through the instrument. One will be passed through the reference and another will be passed through the sample. The reference means, suppose you will make a solution of your sample through solvent. So in the reference you will put pure distilled water, and in the sample dissolved in distilled water. So after passing through the pure reference and passing through the sample containing the solvent, it will be detected and the difference in wavelength will be plotted. The difference in intensity of both the waves will be plotted. And the next one is, the third one is photodiode array spectrometer. In a photodiode array spectrometer, that is also called multiple channel instrument, the radiation output from the source is focused directly on the sample. This allows the radiation of all the wavelengths simultaneously fall on the sample. So in the previous section, the monochromatic radiation will be fall one by one, but here all the radiations will fall on the sample. The radiation coming out from the sample after absorption is made up to fall on the reflecting grating, and the schematic arrangement will be like this. So this is the source of the electromagnetic radiation passing through the lens. So all the radiation containing all the wavelength will pass through the sample, and it will be observed through gratings. Now coming to the analytical application of the UV visible spectrometry. So both qualitative and quantitative applications are there. So this is the last part. So the last part of this application we will discuss tomorrow. Okay.